So we are going to go through some of the math calculation problems just so that we can get an idea of how to do these problems by kinematics. So for number 11, we are standing at the top of a 3-meter ladder. We throw a ball straight up with an initial velocity of 4 meters per second, and we want to see how fast the ball is moving when it hits the ground. We want to sketch the position time, velocity time, and acceleration time graphs for this problem as well. So let's start with that. So for our position time graph, we know our ball is going to start 3 meters above the ground. We're going to throw it upwards, where it's going to slow down until it reaches the top of its trajectory. So on its way up, our ball is slowing down. So we want to draw that graph with our curves getting less and less steep. At the top, our ball is going to stop to change direction, where it's then going to head in the negative direction and speed up as it falls back to the ground. To show this in our velocity time graph, we want to show that we start with an initial positive velocity. So our initial velocity was 14 meters per second. Since we said as it's moving up towards its maximum height, it is slowing down, that means our velocities are getting closer to 0. And it's at that max height that our ball stops and has a velocity of 0. After that max height, our ball is going to change direction and now start moving down or in the negative direction. So now our velocities are all going to be below that x-axis. Okay? And I'm going to want to show that my final velocity is going to be greater than my initial velocity because our graph is not symmetrical and we're moving in that negative direction for longer. So we're going to have more of a chance to speed up there. And then, of course, for our acceleration time graph, that is the slope of our velocity time graph. But we always know that our acceleration has a value of negative 9.8. So for these problems where an object is in free fall or it's in the air, we know our acceleration is always going to be negative 9.8. Okay? So for our graphs, we want to show that our ball is moving in the positive direction first and slowing down. So in our position time graph, our slopes get less steep. In our velocity time graphs, our velocities get closer to 0. At the maximum height, our ball stops and then changes direction to move in the negative direction. So our velocities go beneath the x-axis, and we're speeding up, so our velocities get further from 0. Note, during this whole time, even when we're moving upwards, when we stop at the top, no matter at what point in motion we look at, our acceleration is always at negative 9.8. Okay, so no matter what part of this motion we're looking at, our acceleration is always going to be that negative 9.8. Okay, so now let's go ahead and look at the math for this problem. So we know that we're standing atop a 3-meter ladder, and our ball is going to hit the ground. That means our ball is going to move 3 meters down, or have a displacement of negative 3. We know our initial velocity is 14 meters per second, because that's how fast we throw the ball up. And we want to find how fast the ball is moving when it hits the ground. So we're trying to find our final velocity. We do know something else here, and we talked about this earlier. We know our acceleration is going to be that negative 9.8 meters per second squared, because that is always our acceleration in free fall. Okay. So once I've picked out all the values in this problem that I know, I'm going to want to look at my kinematic equations and decide which one includes all these variables. And that is going to be our equation, our final velocity squared equal to initial velocity squared plus 2a delta x. From here, we just need to plug in the values that we know. So we don't know our final velocity. We know our initial velocity is 14. 2 times negative 8 times the displacement of negative 3. And it just becomes an algebra problem. The tricky thing here is since velocity are squared, we're always going to get a positive velocity. So we're going to end up with a velocity of 15.96 meters per second. But if we look at our graphs, we can see that right before the ball hits the ground, our ball is moving in the negative direction. So all of our velocities are negative, are beneath the x-axis. So we're going to want to add a negative sign in here. Okay. So we know right before the ball hits the ground, our velocity is going to be negative 15.96 meters per second because that ball is traveling down. Okay. And we can see that in our velocity time graph, that our final velocity is going to be a negative value. Okay. Let's go ahead and look at this next one. So this one, we are looking at objects not in free fall because we are not in the air. So here we start a rock slide that has rocks crashed on a 100-meter slope. So here our objects are moving downwards 100 meters, or displacement to negative 100. We know the rocks reach the bottom in 5 seconds. That's our time. And we want to find the acceleration. Again, it is not negative 9.8 here because we're not in free fall. We're not in the air. So right now it looks like we do not have enough information to solve this problem. But we do know something else, is that before the mountain goat starts the rock slides, our rocks are not moving. So that's why our initial velocity for these rocks is going to be 0 meters per second. Okay, so since our rocks were not initially moving, we know our initial velocity here is going to be 0. Okay, so we need to see what equation includes all 4 of these variables, and that is linear displacement is equal to initial velocity times time plus 1/2 a b squared. Okay, so you guys will be given all these equations on the test. You do not need to memorize anything. So in our displacement is negative 100. Our initial velocity was 0, so that whole term is going to drop out. Anything times 0 gives us 0. Plus 1/2 times our acceleration, which we don't know, times our time of 5 squared. Okay. From here, it just becomes an algebra problem. So we need to manipulate our variables to get a by itself, multiply both sides by 2, divide by 25, and we should get an acceleration of negative 8 meters per second. Okay, and this makes sense because our rocks are moving downward and they're going to speed up as they move downward, so acceleration should also be negative. Remember, when your velocities or your movement and your acceleration are in the same direction, that tells you that you are speeding up, which your rocks in this case are. Okay, so we have one more question here. So for this one, we have a dog runs down his driveway with a constant speed of 5 meters per second for 8 seconds. He then uniformly increases his speed to 36 kilometers per hour in 5 seconds. So the first thing I'm going to want to do before I even look at my question is convert this to 6 kilometers per hour. We know when we're doing these kinematic equations, we always want to work in meters and seconds. So figure 36 kilometers per hour and convert kilometers to meters, because I know 1 kilometer at 1,000 meters, and convert hours. So I know that in 1 hour, I'm going to have 60 minutes, and in 1 minute, I'm going to have 60 seconds. So this means if I'm moving at a rate of 36 kilometers per hour, that's going to end up being the same thing as 10 meters per second. Okay. All right, so we want to find the dog's acceleration during the second part of his motion. So this is where he's is running down at a constant speed of 5 meters per second and then speeds up to a final velocity of 10 meters per second. So before we accelerate, we knew our initial velocity was at 5 meters per second. When he reaches the bottom of the driveway, we know his final velocity is 10 meters per second. And this all happened over a time of 5 seconds. And our goal is to find our acceleration. So we need to find a kinematic equation that includes all 4 of these variables. And that is going to be our final velocity is equal to initial velocity plus acceleration times time. Where I know our final velocity is 10, our initial velocity is 5, and this is all happening over 5 seconds. Okay. All right, so we subtract 5 from either side, divide by 5 seconds, we're going to get an acceleration of 1 meter per second. All right, so then for B, it says if he makes it to the end of the driveway in 13 seconds, how long is the driveway? So we're trying to find our displacement here. So here we're going to kind of want to break up our motion into two sections. The first one being when he's running with a constant speed, and the second one being when he is increasing his speed. Okay, so we have 2 different kinds of motions here that we're going to have to find our displacement for. The first one, when we're moving at a constant speed of 5 meters per second for 8 seconds, to get our displacement there, we're going to take our 8 seconds and multiply it by the speed that we were running at. So for 8 seconds, we're running at 5 meters per second. So in the first portion of our motion, we run 40 meters. We then need to see how far our dog moves in the second portion of his run. So in the second portion, when he increases his speed from 5 meters per second to 10 meters per second. So to find our displacement in that portion, we need to use a kinematic equation. So there, we are going to use our equation that delta x is equal to, we have a couple different options, but I'm going to choose our delta x is equal to our initial velocity times time plus 1/2 at squared, because we know our initial velocity, our time, and our acceleration. So we find for the second half of this motion, he is going to run a total of 37.5 meters. So then if we want to find how far he runs in total, we are going to add those two values together, the 40 meters he traveled while moving at a constant velocity, plus the 37.5 meters he traveled while accelerating. And we should find that he travels a total of 77.5 meters. Okay, so since we are not accelerating the whole time, we're going to have to solve this one in two parts. Solve for how far he travels in the first portion of his motion, where he's moving at a constant speed, and then solve how far he travels in the second portion of his motion, where he is accelerating. Okay. Another way that we could solve this one is by graphing. If we were to create a velocity versus time graph, we know for the first 8 seconds, he's running a constant velocity of 5 meters per second. Okay. And then in the next 5 seconds, so after 13 seconds in total, his final velocity is 10. What we could do if we wanted to is we could find the area of our velocity versus time graph and solve for our displacement. So that's another way we could have solved this one. Create a velocity versus time graph to describe your motion. And then if you find the area of that graph, that would also give us a displacement of 77.5 meters. So a couple different ways we could have looked at it. Okay. All right, so I hope this helped. Please let me know if you guys have any other questions. Otherwise, I hope you have a great day.